Okay, everyone. Well, it's 12 o'clock. So let's go ahead and get rolling for the day. So welcome back from your weekend. I hope you had a nice weekend. I want to go ahead and give a couple announcements, and then we'll look at our riddle, which is great. And then we'll jump into worksheet number two. So in terms of announcements, keep in mind that we have that last structural tutorial and the quiz that's due tonight. And then there's a quiz that's due tomorrow as well, quiz 4. So you want to make sure that you keep those on the forefront of your mind and get those done if you've already gotten them done. Okay. Um, Last Friday, also, the university made its announcement when phase 3 classes will be able to come back in a face-to-face setting. I went ahead and followed that up with my own announcement on Canvas, telling you what all of that means for this class. And specifically for our section 00 on Mondays, what that means is that actually next Monday, we will be doing a Zoom, instead of a Zoom, we'll be doing face-to-face in Yates 104, okay? The following Monday, right after that, you'll take that Monday off, okay? The whole class is actually taking, we have a little bit of break when we have exam week, okay? But the Monday section is always one week behind because of Martin Luther King Day. So, okay, so next week in Yates 104 for the first time, which will be awesome. Okay, and we'll go from. Okay. Okay, I think that does it for announcements for the day. Let's go ahead and look at our riddle. So, a doctor and a bus driver are both in love with the same woman, an attractive girl named Sarah. The bus driver had to go on a long bus trip that would last a week. Before he left, he gave Sarah 7 hours. How do you do this? Anyone want to mic in and tell me or chat this one? Okay, I got an answer in the chat. Let's check it out. An apple a day keeps the doctor away. Exactly right. Exactly right. I know it's really, really lame. Um, but I am a dad after all. I get made fun of by my kids for these kind of things. So, so, okay. All right, let's go ahead and move now uh, into our worksheet. And we're stepping back all the way to chapter 2 and really chapter 4 material. I know that you've all started now chapter 5, which is great. That's an awesome set of lectures in Echo 360 and structural looking at the protein structure. And our next worksheet number 3, will address some of those topics within that. However, when we look at today's worksheet, we want to go back to chapter 2 and chapter 4. And there was lots of really actually interesting things that we're going to bring forward into chapter 5 from those chapters. For instance, non-covalent interactions is enormous when we start to think about protein structure and what holds it together, okay? But another topic that we covered in both of those chapters was acid-base chemistry. And that's going to be very important for us to understand both protein structure and protein function moving forward. And specifically, we kind of focused in those chapters on how do we use PK to determine the protonation states of a particular functional group. Okay, and then of course in chapter 4, we looked at functional groups on amino acids. Right, so today in our first activity, what we're going to be really thinking about is what is the PK? So thinking more about theory and in the theoretical behind PK, and then we'll move into activity number 2 behind the kind of the utility. How do we use it in combination with pH to determine protonation states of a functional group? Okay, so that's what we're going to be doing, right? So let me go ahead and turn off my video here so I can write on my screen. If I did this with my video on, you'd be staring at my ceiling, which is no fun. So let's go ahead and look here at the 2 molecules that we'll look at in activity number 2. I'll just draw them structurally so you can kind of compare them. And I'm going to go ahead and draw them in what would be considered the fully protonated state. Okay, so one of these molecules is going to be propionic acid. Okay, and it's shown right here. Right, now the other molecule that we'll compare this to for our understanding of PK will be glycine, the amino acid glycine, which is a very simple amino acid when you look at its side chain, okay, but it is still amino acid. Okay, and when we look at these two molecules, propionic acid on the top, glycine on the bottom, they're very, very similar to one another from a structural standpoint. In fact, the only real difference here would be this methyl group at the end, okay, versus at the end of glycine. Right, so those are the structural differences that we'll kind of highlight in this activity. Now, the other thing that we want to keep in mind is the difference in pK. Somewhat interesting here. The pK of this molecule is 4.87. Now, that's in reference to, just so we have some concept of that, that's in reference to this carboxyl group. Okay, that's for the pKa for that functional group. Okay, that will be true down here too. We could look at pK1, subscript 1. It denotes that this is for this carboxyl group. Okay. And what you notice here is that the pK of the carboxyl group in propionic acid is almost 2 times larger than that of pK1 found in glycine. Okay. So given that, what I want you to go ahead and do is break up into breakout rooms, right? We'll I'll open those here in just a moment. Read through the instructions and essentially answer the questions at the end of that activity. What does pK mean? Which of these has a higher affinity for a proton? And read through those questions. And we'll also look at some of the structural differences and how they can relate to these PKs. Okay, so keep in mind here, we're thinking about what does PK mean, all right? That's kind of how we're approaching this, okay? All right, so let me go ahead and open the breakout rooms. Once again, I'll give you the option to choose your own breakout room. Okay, that does lead to some log jams. It always has. Okay, and so as I notice those log jams starting to occur, I'll go ahead and start just assigning people to rooms. Okay, all right. So the rooms are now open. So go ahead and start to put yourself in a room if you have that option. If you don't, just wait out here. Wait for just a little bit, and I'll get you in a room. And you have 8 minutes, by the way. All right, I'm gonna go ahead and start assigning people to rooms just to get this process going for people. Hi, Jessica. How you doing?
I am doing good. Very productive Monday so far, so
Oh,
I'm in a good mood.
that's good. That's good.
Yeah.
I made you a co-host, so you should have the options to get in the rooms now. So
Okay, sweet.
yeah, it's always nice when Monday's productive. My Mondays are always hectic, so I have a lot going on Mondays. So anyway, how's your weekend?
It was good. It was actually my birthday weekend, so I had a lot of fun. Yeah.
Oh, well, happy birthday! Happy
Thank
birthday!
you.
Yeah.
Yeah, it was good. I wasn't expecting a whole lot from it just because of COVID. There's not a lot to do, but my family came out for a day and we had dinner. I had dinner with my roommates. So yeah, it was a lot of just catching up with people, which was fun.
Yeah, that is nice. That's cool. So
Mhm.
yeah, the COVID has kind of made it hard to go out and do something. So breakout rooms. We've done a couple of those since COVID has happened. So you take a group and do that. That's kind of a fun thing to do. But so anyway, So restaurants are kind of hit and miss. Some of them are open, some of them aren't.
Mm-hmm.
So
Yeah, we ended up going to Union, which they have like the outdoor patio, which is open, so we were all comfortable with that. So
okay,
that's
cool.
a choice, yeah.
Yeah, very cool. Okay, well, let's go ahead and start to head into some rooms. I'll start top, and if you start bottom, and we'll kind of work our way into the center, okay?
Perfect.
All right. Hello, everyone. Is there any questions in this room that I can help people out with?
Yeah, I
Yeah.
think we're doing okay.
Well, we were just talking about which one will require more protons in the solution,
Okay.
and would it make sense that the lower affinity molecule would require more protons?
Yeah, exactly.
Okay, I just wanted to make sure.
Yeah, no, you got it. So the idea is that, if you put a bunch of, you just like pack the thing with protons and those start to stick to things, right? So things that are things that have a weaker affinity require more protons surrounding them so that they can then form that bond with those protons. So whereas something with a weak affinity, a really strong affinity, doesn't require nearly as many protons surrounding. Yeah, very good.
Yeah, okay, cool. That's what we were thinking. We just wanted to make sure.
Yeah, you got it. All right, well, I'll go to the next room, okay?
Thank you.
Yeah, no problem. Hello, everyone. Is there any questions in this room that I can help out with?
I think we were kind of confused about like understanding affinity,
Okay.
differentiating between the two.
Yeah. So affinity just simply means strength of interaction between two things. And that's really what we kind of mean from a chemical standpoint, what affinity is, right? So in this case, because we're talking about acid-base chemistry, thinking about the strength of interaction, in particular on those two molecules, the oxygen and the hydrogen in our carboxyl group, okay? And so that's what we mean by affinity. And when you start to think about this, okay, from an acid-base standpoint, let me ask you all this, okay? Given that definition of affinity, which of these has a higher affinity? And how would you know these molecules? What do you think?
I was thinking you were leaning towards the second one.
Mm-hmm.
The nitrogen.
Okay, so the glycine, so the one with the lower pK.
Mm-hmm.
Okay, so
We
actually,
have that backwards.
yeah, you jumped in the wrong direction on this one. That's okay. That's why we do this, right? So the larger the pK, the greater the affinity of that particular conjugate base for a proton. Okay, so when you think about it this way, let me put it this way: bases are things that take protons out of solution because they have a really high affinity for protons. Bases will have a really large pK. Okay, so they'll have pKs above 7. Okay, and so if you just think to yourself, okay, base is a proton acceptor, it takes protons, meaning that it finds protons in the solution and sticks to them. Right, that's another way to kind of keep this straight. Okay.
Okay. Thank you.
Yeah, no problem. So we only got a minute left, so we'll kind of expand on this. We'll talk about, well, how much protons we need in the surrounding environment, but let's do it all as a big group, and hopefully that will help out as well. Okay.
Okay.
Awesome. See you in a bit.
Thank you.
Mhm. Okay, so I think that most people have filtered back into the room now, so we can go ahead and talk about this as a big group. Okay, I didn't get through too many rooms. I had some good questions on the rooms I was in. And so, let me do this. Let's start off this way and just start off with probably what would be considered a fairly straightforward question. And that is, well, which of these molecules, okay, considering the pK values, is going to have the greatest affinity for a proton, meaning which conjugate base has the greatest affinity for the proton. Okay, the top one or the bottom one? What do you think? So just fill up the chat. What do you think, top or bottom? Or you can mic in and say what you want, what you're voting for. So we got a lot of answers here in the chat starting to populate. All right, so yeah, so most people are saying top, right? Okay, the top one. Okay, great. So when you look at this, that's right. Okay, if you went back to your notes, maybe you might have noticed that, okay, it looks like large PKs mean high affinity. Okay, and that would be something that you can just kind of remember. Large PK means high affinity. Okay, now what I want to go ahead and do is talk a little bit more about, well, what does that exactly mean? And how do we kind of work with that? Okay, and so let's just go ahead and do this. Okay, and let's start with this statement, okay? So PK, what does that exactly mean, right? We say that the larger ones mean that conjugate has a higher affinity for a proton, but what does that exactly mean, that PK? Okay, now, before I write this out though, I forgot, I should state this, because I think that this is something that students, have a somewhat of a struggle with, and that is, what is this idea of affinity? And affinity just simply means how strongly two things are going to interact with each other. Okay. And it's not something that, quite honestly, you talk a lot about with acid-base chemistry, but I kind of like to use acid-base chemistry to lay the groundwork for later discussions when we talk about proteins affinity for ligands and enzymes affinity for substrates. Okay. We just simply mean the strength of interaction between those two things. Okay, in this case, it would be a proton and a conjugate base. And what our pK simply means is this: it is the pH. Our pK is equal to the pH where the concentration of the deprotonated form is equal to the concentration of the protonated form. Okay. So we can say for this top molecule, right, it's got a pK of 4.87. That means that at a pH of 4.87, then the concentration of the conjugate base, the deprotonated form, is equal in concentration to the protonated form. Whereas below, the glycine molecule, that carboxyl group requires the pH quite a bit lower, 2 units lower, to reach that same, or to have that same concentration of conjugate base versus concentration of protonated form. Okay. Now, given that, let's take this a step further and hopefully understand a little bit more about affinity. Right? Which of these then requires more protons in the surrounding to remain protonated? The top one or the bottom one? Okay, so let me ask that again. Which one of these requires more protons in the surroundings to maintain the protonated state, the top or the bottom? Okay, and so I'm starting to see some answers on here on the chat. Okay, so let me check those out. Yeah, so 3 answers already for the bottom. Okay, and that's right. Okay, so that's going to be the correct answer with this, right? Again, if pH is equal to pK, right, coming back to this statement right here, where they're an equal amount of protonated and deprotonated form, that means that this pK, right, or this, yeah, the glycine molecule with this pK being low, that means it requires a significantly lower pH, which means that it requires larger amounts of protons in the solution to maintain a protonated state, right? Low pH, remember, means lots of protons. Right, now let's go ahead and draw this out. I think that we can take this even a step further. Okay, and just draw this out in a beaker. And hopefully put this visual in your mind. Again, this will lay some foundation for later on, okay? But let's think about a beaker full of water, okay? And we'll just say that there is some acid-base chemistry going on in it that would be consistent with this, right? HA goes to H plus A minus, okay? All right, and now, just a second, I think I got a question in the chat. Let's look at this. All right, wait, just checking, lower or more protons. I think I misheard, or maybe I misspoke, right? So let me say this, okay, because sometimes it's easy to get confused. It takes this one, the glycine takes more protons in the surrounding solution to maintain the protonated state. So it'll be more, okay? So I hope I said that, okay? Right now, coming back to our little visualization here, let's just do this. Let's draw a scenario where we have HA, there's an HA molecule, and here's another HA molecule. And then we'll draw some A minus in here. Okay, so there's an A minus, and there's an A minus, okay? Okay, so I've got them equal to each other, right? So this would be the standpoint that's described up here where they're in equal concentration. Right now, if I were to then just use dots, let's just say that the little dots represent protons, okay? When we start to think about that question that I asked, will it take more or less protons in the surrounding solution to keep it in the protonated state? When we start to draw these dots here, okay, it would be that glycine molecule that would require me to draw more dots, more protons in the surrounding solution to maintain the state that's being shown here versus the top, right? And the reason being that I would have to have a pH of 2.34 to keep HA and A minus equal to each other, okay? I could just keep drawing and go on, okay? Now, here's the interesting thing here, okay? As we start to then, let's say, remove protons from solution, let's stick with our idea of glycine here. As we start to remove protons from this, so let me just start to get rid of some of these, right? What would happen here is this. This would go down, and this whole thing would shift in that direction, which means that when I start removing protons, I would probably, not probably, I would lose some of that and gain some of this in its place, okay? Right? So that's the idea of a titration, that you're removing protons and you start to deprotonate things, okay? Now, that's gonna, like I said, this visualization, okay, it will hopefully be helpful to us later on, because later on we'll talk about, like, let's say, enzymes and substrates. And we'll think about an enzyme with a high affinity for a substrate takes less substrate in the surrounding environment to bind to it. And that will give some idea of the strength of interaction between, let's say, an enzyme and a substrate. And we'll use some, that will actually be called the Km. We'll use an equilibrium constant to determine, okay, which enzymes have stronger affinities and weaker affinities for substrates, okay? But for here, we're using pKs, okay, and this idea of affinity. And, you know, when you think about it this way, this glycine molecule, okay, here, it just requires a lot more protons in the solution for those protons to stick to that oxygen, okay, as compared to the propionic acid, okay? So you have to really jam it full of protons to get them to stick, okay? All right. Now, are there any questions on that before we move on to the last question in activity number 1? No? Okay, it doesn't look like it anyway. And feel free again to mic in or write questions on the chat. It's perfectly acceptable, okay? All right, now let's do this last one, okay? And there's kind of just a small point that we want to make, and that is, well, why do you think that these two are different, right? And by these two, I mean these two pKs, when we look at the structures of these. Now, here would be the take-home message from this. The take-home message is that pKs are environmentally sensitive, okay? Meaning that the value of a pK can change based off the environment that it's put in, okay? Based on the environment that the functional group is put in, right? And so what we have is two functional groups. They're both carboxyl groups, okay, that I've circled in red here, and here that I just put stars by. But those two functional groups are in different environments, right? One of them, in glycine, is in an environment where there's this positive charge over on the left-hand side of the molecule. That positive charge is not there in propionic acid, and that positive charge is actually what causes the PK to drop. Okay, if you want to think about it this way, there's two ways to really explain this. That positive charge, you could think about it as actually repelling the proton found on the oxygen. Protons are positively charged, so there could be a repulsive force there. Okay, another way to think about it is to think about electron drawing power of the nitrogen. The nitrogen can draw electrons to itself, okay, and that will weaken the bond between oxygen and hydrogen. Okay, so those are two decent ways to think about this. We're not being physical chemists in this explanation, but that's decent enough for this. Again, the main point being that functional groups, PKs, are environmentally sensitive, okay? And these two carboxyl groups are in actually quite different environments because of that positive charge, okay? Okay, now let's do this, okay? In the interest of time, let's move on to activity number 2. And activity number 2, we're really thinking here about the utility of PKs. How do we use them? And how do we use them specifically to predict protonation states of functional groups in a certain molecule? And so we're going to look at this amino acid lysine. The structure that you see drawn over there is at the pH of 7, and it gives you the values for each of the PK groups. The instructions are pretty straightforward for activity 2, so I'll go ahead and let you read through them with your group and then work on that. And of course, we'll all come back together. I'm going to give you 10 minutes this time because I think this is a little bit more challenging to do. There's a little bit more to do here. Okay, so let me go ahead and open the rooms for everyone. You got 10 minutes to predict the form of that amino acid at a pH of 11. Okay, and all the rooms are now, oops, wait. Well, I just, go ahead. I only gave you 8 minutes, but I'll give you 2 extra minutes, okay? All right. Forgot to extend the time on the rooms. Okay. I only got through 2 rooms. The last one.
I think I got through 3.
Okay.
Oh no, 4. I did good.
You did better than I did, yeah.
I mean, I wouldn't say it's totally good because the first room, like all of their videos were off. Nobody was talking. And I said, like, do we have any questions? And nobody answered me.
No one answered you even.
Yeah, nobody. Usually at least one person's like, no, I think we're good.
Yeah, this is the worst, right? When you go in there and this is like everyone's silent. So, yeah, it's not good. And they won't even say anything. It's like, you can, there's only like 3 people in this room. You can go ahead and talk. So anyway, yeah, it's kind of a bummer. So it's interesting because I think the Zoom is almost a better environment in some ways to try and do this kind of stuff than at least the face-to-face right now because of the masks. But people don't like doing it. So what are you gonna do?
Yeah, that's true. Yeah, I remember last semester I just sat, like 6 feet away from my one friend that I knew in there and just like whispered to her the whole time.
I know,
It
yeah.
was dead silent. That was the best we could manage.
I know. And it's like almost, it was like, I'm trying to encourage people to talk to each other, but it's just one of those environments where you're like, I don't know if, especially if you don't know anyone, right? You're like, is that person going to be offended that I'm talking to them? Or they think, it's the whole COVID thing makes everything difficult. So, okay, well, I'm going to jump into a room or 2 here and see if I can't get through more than 2. So,
Cool.
right. Hello, everyone. Any questions that I can help out with at this point in time in this room?
I don't know. I'm doing good so far. I don't know if anybody else has any questions.
Anyone else have a question or two? Where to start?
So
I'm sorry, Emma, what'd you say?
I'm just drawing it still, so I'm good.
Okay. Okay, well, if you do have questions, let me know. So I'll jump out and go find another room, see if they have some needs, okay?
Sounds good.
Right.
Yeah,
that
just
makes sense.
I just don't know if we would. Yeah, no, it makes sense, but do we have to draw the lone pair?
We probably could just for our own sake. We're counting the number of electrons.
This is what I drew.
That's what I had, yeah.
Yeah,
Awesome.
I just did the CH in the same one, but I'll redraw it out differently.
Yeah, that's good. Any questions in here that I can help out with?
I think we problem solved through it.
Awesome. Great. Well, we'll see you in the big room then, okay?
Thank you. Thank you.
Yeah, and the reported time, you get 2 more minutes. I forgot to give an extension, so other people will need a little bit more time. So, okay.
Okay.
Is there any questions in this room that I can help out with?
The only one I had was, are we supposed to remove the positive off both of the amino groups?
Well, so what do you think? Let me ask you this, Becca. Do you, at a pH of 11, do you think that they're going to be protonated or deprotonated?
Deprotonated?
Yep. Then yes, if you think that they're going to be deprotonated, which I agree with, then yes, you would remove the positive charge off of both of them.
Okay, thank you.
Any other questions?
I think that's it.
Okay. Awesome.
Thank you.
Yeah, no problem. Well, I'll go to the next room. Okay.
Alrighty.
Any questions in here that I can help out with?
I don't think so.
Yeah, I didn't have any yet on this one.
Okay, great. Alexia, you they cut out. Did you say you had a question?
Oh, sorry about that.
Okay.
I was. I don't think so. I'm still trying to.
Still kind of powering your way through it?
Yeah, a little bit.
Okay. Okay, well, go ahead and keep working on it. We'll all talk about it as a big group anyway. It says we got 50 seconds, but I'm going to give you an additional 2 minutes. So you've got a little bit of time to work on it. So.
Okay, perfect. Thank you.
Yep.
You think it's worth trying to go in one more room, or 20 seconds not enough? I can't hear you.
I'm going to give them an additional 2 minutes. So yes, it would be probably worth it. Any questions in this room? that I can help out with?
I think for the most part, we got it. Just understanding that just at the pH of 11 versus 10.53, it's obviously not going to be a very predominant form, but it's still a predominantly negative one. Is that correct?
Exactly. So it's not, like you say, very predominant, but it will be predominant, meaning greater than 50%, right? So we'd have to use the Henderson-Hasselbalch equation to find out exact percentages. But yeah, it would be predominant. So yeah, nice job. Okay, excellent. Well, we got only about a minute left, so I'll be closing the rooms here in just a second, okay? Nice. Okay.
Thank you.
Yep, see you in the big room. Okay, so everyone's filtered back into the rooms now. Okay, we're in the big room. And we can start to look at then how do you do this, right? And had some good conversations. Seemed like actually most people are starting to gravitate towards how to do this, right? You've probably practiced it. Maybe you've had some Q&A sessions about it as well. But let me go ahead and talk a little bit about this, and then we'll let you go. So I think that probably the best thing to think about, okay, and maybe the best question to answer is, well, where do I even start with a question like this, okay? And that always is somewhat of a difficult thing to think about when you're first being exposed to questions like this. But I think the best place, and let me go ahead and tell you what I would do. I think the best place to start with something like this is actually to start by drawing the molecule at a pH of 0. So let me go ahead and do that. Okay, so think about a pH of 0, just going back to this discussion here. When you have a pH of 0, you put so many protons in the surrounding solution that everything is going to be protonated. Okay, so if we were to draw our lysine molecule at a pH of 0, it would look something like this. Okay, it would have a protonated alpha carboxyl group. Oops, need another oxygen there. There we go. It would have a protonated alpha amino group. And then it would have a protonated side chain, or R group. We'll use some shorthand here. 4 methylene groups there. And then we'll put NH3 plus here. All right, and this is what the molecule would essentially look like at a pH of 0. Now, I mentioned this before I sent you off into the room, okay, but the form that you see on the activity 2 and on the worksheet is actually at a pH of 7, okay? So keep that in mind, and that's true really of most amino acids in the structures that we give, okay? So that's certainly true of the book that we're using. All the figures that you see are the predominant form at a pH of 7 because pH is a biologically relevant pH. Of course, pH of 0 is not. But it's kind of nice here to draw it at a pH of 0 and just say, okay, I've got protons and everything, right? And then what I do, right, just going back to this idea, remember if I start removing protons, right, then I start to shift in the direction of deprotonation, okay? And so when I start to think about this, I need to get all the way up to pH of 11. I can move mentally in my mind all the way up to pH of 11. And every time I encounter a pH that is equal to the pK, I start to remove the proton off of that group. Okay, so for instance, right, this first group, the alpha carboxyl group, pK1, it has a pK, or its pK is 2.18, correct? Let me look. Yep, 2.18, okay? Which means that when I get to a pH of 2.19, the predominant form of that carboxyl group, okay, and the molecule that has that carboxyl group in it will be deprotonated, and that will have a negative charge. So I'll go ahead and draw it over here at a pH of 11, because at a pH of 11, we're way past that pK. So we're definitely deprotonated this, and this will have this COO minus. Okay, look, okay. Now, I can do that, of course, for the alpha amino group. And the alpha amino group is going to be the pK2, and that will always be the case with the alpha amino group. It's pK2. And in this case, the alpha amino group would be 8.95. Okay, so as I go up to pH of 11, of course, I'm going to go past 8.95. I'll get to 8.96, and then I'll deprotonate that. Okay, and when I do that, then the deprotonated alpha amino group will be NH2 with no charge, neutral. Okay. Now, I keep moving, okay, and come to this, the pKr. Not all amino acids have a pKr, but this one does, and it's 10.53. So it's close to 11, but it's still lower than 11, which means that at a pH of 11, of course, I've removed that proton. Actually, at a pH of 10.54, the predominant form would have a deprotonated side chain. Okay, so I'll put this here, CH2, 4, and then I put NH2. Okay, now interestingly, one of the rooms that I went into said, they said this, well, the predominant form at a pH of 11, right, it wouldn't be that predominant, right? It would be closer to the 50%, and that's right, all right? What they meant by that is to say that the form that we drew here at a pH 11, this is at a pH 11, if we were to look at the percentage, it would be greater than 50%, but it wouldn't be like 99% of the molecules would look like this at a pH of 11 because we're still pretty close to this pKr, okay? We're not going to get into the exact percentages. We can calculate those using the Henderson-Hasselbalch equation, but we're not going to get into calculating exact percentages in this class, okay? All right, so this is what it'd look like at a pH of 11. Now, of course, the question says, well, what's its formal charge? Well, that's fairly straightforward. We just need to add up the charges on this. We have a -1 here, no charge, and no charge, which means that -1 would be the formal charge of this molecule, okay, at a pH of 11, okay? And that's, I think, probably the best strategy to use when you start to think about how to do these types of problems, okay? Just think about the molecule at a pH of 0, put a proton in everything, and then start to remove protons from functional groups as you get to pHs that are above their pK, okay? And then, of course, calculate formal charge from there, okay? Now, this will be a really important skill as we start to do this in proteins. We'll think about, you know, whether something is protonated or deprotonated so it can form ionic bonds, or whether it can, you know, do lots of other things. Maybe it will participate in something called acid-base catalysis that we'll talk about in chapter 6. So, all right, so that's all we really need to do for activity number 2. Okay, are there any questions on this before I go and open up a poll everywhere question? Anyone have any questions? You never know how long to have an awkward pause of silence. So, okay. All right. I think that was long enough. If you do have questions, I would certainly encourage you to chime in right now or hang out. I won't leave the Zoom session until everyone's gone. Okay. Oh, it looks like we got one on the chat. Let's see here. Okay. So you remove protons on each pH goes up. That's correct. Okay. So if you come back to this whole idea here, right? If you remember, I'm drawing these blue dots here. Okay? And if I were to then start to say, let's remove those blue dots, some of these, right? As I do that, oops, I didn't mean to remove that, but as I do that, then what I do is shift this in this direction, which means I get more and more deprotonation, okay? So as you go up in pH, you're removing protons from the surrounding solution, and that's why you shift it over to the right, okay? So very good, right? Okay, let's see. Would you ever remove more than one proton? From a functional group, so it depends on the functional group, honestly, right? So from our acid functional groups that had to have protons removed. So we did in that, but like for instance, an ammonia group, you'll never remove that. It won't go to NH1 and then -1. Okay, that's not a stable form of the molecule. Okay. Right now, just a second, let me do this. I think that people are starting to leave, and I want you to participate in the Q&A. So let me share my screen with that. Okay, and open up this poll everywhere question here. Unlock it and activate it. Okay, so think back to last week. Think to the things that you're doing. Even maybe you did something before coming to class on Echo 360, and get back to us on this. What do you think? What is the thing that's least clear to you? And we'll start to think about getting these into our Q&A sessions so that we can get your questions answered. Okay, so go ahead and type out an answer for me. And if you see something, yeah, memorizing amino acids is least clear to me, and that's the one I want, then go ahead and vote on that or whatever, or find triangles. Okay, so all right, and then you are free to go. Like I said, I'll hang out and answer questions until everyone's gone. Okay, all right, we'll see you all. Take care and have a good week. We will see you face to face next week. I'm looking forward to it. Okay, all right, bye.
Are the Q&A questions for points, or are they?
No, not at this point in time. The Q&A questions that we've not been taking those or anything to that effect. We're just trying to answer in the Q&A session. So this way, when students come, we already have kind of a pre-understanding of or what questions are in students' mind that we'll start to answer those. So what we probably do face-to-face, Zoom is a little bit clunky, so I haven't been doing this, but we have like poll everywhere questions that are for credit when we get to face-to-face. Zoom is kind of preventing me from doing that. It takes too much time to do. So yeah, good question though. Yeah.
Okay, thank you.
No problem.
Can I just ask you a quick question? So if we aren't given the pKa for the different functional groups on a molecule, how would we know the priority in which to deprotonate or protonate, or is that something we wouldn't necessarily need to know?
You wouldn't, so you couldn't determine that without pK. So I will give you, like, if you look at the practice exams or the practice exam, it has this huge list at the very top of all the amino acids and their pKs. So I will give that to you on the exam. So yeah.
Sweet. Thank you.
No problem. Okay. Henley, do you have a question for me?
Sorry, I'm just trying to look. There was a question I had for you, and I'm just trying to find where exactly it was. So sorry, give me just a second.
Yeah, no, go ahead. Take your time. I'll hang out. Jessica, you can probably take off if you need to.
I just had a quick question actually. So for next week in person, like, do you want me to show up early at all, or just kind of?
I mean, early enough, right? I mean, 2 minutes early is enough probably. So you don't need to get there super early. So okay. Awesome.
Sweet, I'm excited.
Yeah, all right. We'll see you next week.
All right, see ya.
Bye.
Bye.